So let us first write down the equation according to the Coulomb. Then we can quickly see what to do with the value of k or how to understand. Now this is a scalar equation that you have. Now the points to be noted before we can understand this equation is the following. So the first point is that there is no idea of how much charge we have when you are performing an experiment, which means that we don't have a unit of charge with us. So this is where the first trouble is. So this is the first point that you have to remember. The second point about this equation is the following. So the second point to be noted is, from the experiment, these are experimental evidences. From the experiment, what all is observed is that the force acting between the two charges Q1 and Q2 is along the line joining them. So this is not a trivial always, but this is very important that it has been observed experimentally. So that is the conclusion. The conclusion coming from the second point is important, even though it looks very simple one. Simple one means the force acting between the two charges is along the line joining them. Now that statement looks very too simple, but the conclusion is a very important conclusion. It talks about the symmetry of the space. So space means what? The space in which you are living. It's a three-dimensional Euclidean space that you are living. No, that space is isotropic in nature. That's the conclusion. So what do you mean by isotropic? Isotropic means that there is no preferred direction. All directions are equally the same. That's the meaning of isotropic. Every direction is identically same. Your conclusion is the following. You travel in any direction in the earth. Okay, or let us say from your house, you travel in any direction along a particular straight line for exactly 100 km. Every time I travel 100 km, I will use only 1 liter, which means that the direction doesn't enter into picture. That is the conclusion. Petrol consumption is independent of the direction. That is your conclusion after doing this experiment. In which direction you are going to travel, what all it matters is only how many kilometers you traveled. Only that matters. So that is a similar situation in this experiment. The force between the charges is acting only along this line. Any other line it doesn't prefer. So therefore we say that nature doesn't prefer a particular direction for the force. Only allowed direction is the line joining them. And therefore this gives a conclusion that space is isotropic in nature in this particular case. But this is not always true when we see magnetism. So later when we are going to learn something about the spin of the electron, so right now we are not going to see that, but in a later course, for example, when you are going to study about the spin of the electron, there will be a magnetic force between the spin. Okay, right now we are not going to do, but when you are studying that, you will read that the force between the two spins will not be the line joining the two spins. So that is the story that you are going to see much later in maybe in another course. So in order to make a contrast now itself, I am giving you the information that this is a very important point which is special to this particular situation. And this is very similar to the case that you are going to have two gravitating objects like a sun and, for example, the earth. If you are going to have the sun and the earth, for example, and you know that what is the line of attraction? The line of attraction is only the line joining them. So only if you draw the line between these two, along this line only force acts. Force doesn't act in any other direction. So these are some special properties of this particular 1 over r square potential. So you are 1 over r square force. So this is we say that this force is, we will write like this: force is proportional to 1 by r square. So the 1 by r square is what we read as 1 over r square force. So it has some special property like this, and later we are going to see that this is possessing the conservative nature. So this is the conclusion now. So coming to the point, okay, we are discussing about the second point here. The conclusion from the experimental evidence is that we have our space being isotropic in nature, which means that there is no preferred special direction. That's a very important conclusion. This is the second point. We'll come to the third point now. The first point says that you don't have any idea about how to measure the charge. We don't have in what unit to measure. We don't know. Suppose if you measure, even if you say that, okay, I will measure, in which unit you will measure? People don't have any unit on how to measure it. So there is no idea. And in this particular situation, how to fix K? Fixing K means how do you give the value for K? What K should be the correct value in order to describe the real situation? So that's the question. And to address this issue, people have evolved over a period of time. Over a period of time means, remember, all the way from 1785, all the way from that time to the Maxwell period. You first tell me in what units you are going to measure the charge. If you tell that, then we can fix the value of k. That's what the meaning of the statement. But just now you have seen that we don't have any idea about the measurement of charge. So we don't know in what unit we have to measure the charge. In such a situation, how to fix the value of k? So that is the kind of trouble that we have in fixing the value of k. So the idea is that, okay, let us fix k equal to 1, but then, so this is the first choice. You fix k equal to 1. That is the easiest choice that you can have. But then remember that the choice of k depends on in which units you are going to measure, and therefore you first propose in what unit you are going to measure. So we say that, okay, let us make the measurement of charge in the units of stat coulomb. So remember the name, it's called stat coulomb. This is very important. CGS ESU. ESU means electrostatic unit, and that is what is the stat coulomb. So stat coulomb is actually electrostatic unit. That is the meaning of this ESU. An alternative name is the CGS Gauss unit. It's also known as the Gaussian units. So this is one plan. This works and it works well. Okay, this fine. It works nicely. And remember that this is not, you should not consider that the CGS unit means something dead old unit and you should not read that. No, that kind of concept you should not have. So what happens actually is that in the school education, the SI units are introduced so that what happened because of that reason is that among the students or among the youngsters, the SI unit is the most popular unit. At the same time, they may also have an idea that CGS units are outdated and they should not use it. Is not so. It's neither outdated or there is no such concept as you should not use it. Right. So this is your gram. Remember that the CGS in that centimeter gram is practical unit. So they are practically comfortable. So as long as things are comfortable, people will continue to use. Therefore, CGS unit is not a dead system. It is still alive. In the electromagnetic theory, CGS unit is a preferred unit when compared to the SI unit. That's very important because when you are going to study, for example, quantum electrodynamics or the special theory of relativity, for example, or if you're going to see the relativistic transformation of the electromagnetic phenomena, at that time CGS units are preferred units when compared to the SI system, because SI system of units there are so many other constants floating around that makes it little bit cumbersome to work, whereas the CGS units are comfortable. So people always see which is more comfortable rather than sticking to the SI system. And you can see that when you are fixing k equal to 1 over 4 pi epsilon 0, the unit of the charge will be in the coulombs. Okay, not in stat coulomb. So that is the difference here, which means that this is what is known as the SI system, or this, what do you mean by the SI system is, you have the standard MKS, which is the meter, kilogram and second, but this is not sufficient. Remember what do you mean by that? MKS is not sufficient. You need an additional unit in order to describe the electromagnetic phenomena. So I am writing a here. Okay, so there is a for ampere. So MKS system of that, MKS means you take it from the mechanics, the meter, kilogram and second, and to the mechanics units you have to add one more unit, what is known as the ampere. Then it is known as the MKSA. That MKSA is what is known as the SI system of the units. So as you can easily see that ampere is added. So this is ampere. So why I am writing once again here is that you have to get a little bit of surprise when you write, because we are talking about coulomb here, and therefore you should ask, why don't you write MKS C you have to write, because coulomb is the one that you are going to attach. No, so surprisingly coulomb is not there here. So the C is not there. You are going to introduce ampere here. So that's because people have studied electricity first and then followed by the magnetism, which is given by, as you already know, ampere, and the Biot and Savart. Biot-Savart law and the ampere law gave the force between the two wires. So that has been studied, and based on that, which means that based on the magnetism, you fix the value of k. You see how the story goes. The fixing the value of the K here requires the force due to magnetic field, which means the current is coming into picture. So this requires, this kind of refinement is required because electricity and magnetism were intertwined. That means you cannot separate the electricity and magnetism. Wherever there is electric phenomena, there magnetic phenomena is there without your knowledge. So it's basically involved in a relativistic way. So right now you don't worry now, but try to understand that what is called electric field can also be called a magnetic field. It's only a relativistic effect. So the details we are not going to see in this particular course, but at least you try to understand that electricity and magnetism are just two sides of the same coin. It's not a different coin. You take a coin and see the front side, it looks like electricity. Same coin you see in the back side, that looks like magnetism. How it looks like is, it's a relativistic transformation, it happens. So those details we will be learning only in the graduate course. But now I am giving you this brief introduction in order to make some kind of justification why I have written ampere here. That's why ampere has come into picture, because this is a electrical current, and when you have the electrical current, there is a magnetism. When there is a magnetism, the force is magnetic force, and from the magnetic force you bring the value of K for electrostatics. So you see how the connection is going like that. So that is how it works actually, and because of that reason only these quantities has entered into picture. So we will not enter into the derivation of how this happened. That happened in historically over 100 years of time, and the more details are involved in the calculation. So right now that is not important for you. Now what is important is that you have two choices of fixing K. The one choice is this one, the second choice is this. Let us say that the force is 1 dyne. So 1 dyne of force will be obtained equal to K. I am going to fix K equal to 1 here. So 1 into, so 1 is fixed because K equal to 1 you are going to fix like that, into Q1, Q2, and you have already made a statement that Q1, Q2 will be measured in stat coulomb. So I have to write down that this is 1 stat coulomb multiplied by the second charge also you take exactly 1 stat coulomb. So I'll write like this, 1 stat coulomb, then divided by, we are using the CGS system, therefore you must get a centimeter. So let us have a separation distance of 1 centimeter and then square this. So this is your Q1 and Q2. If you are going to make an experiment like this 1 stat coulomb you are going to take, and then 1 centimeter you are going to maintain, and then I also fix the value of K equal to 1. If all these things happens, then I must be able to measure 1 dyne of force. You can always make a measurement and verify whether you get 1 dyne or not. So once you get 1 dyne of force, when there is a 1 centimeter distance, then you know how much charge you have taken, and that is called 1 stat coulomb. We are going to say that 1 stat coulomb of charge is that amount. So that amount means which you do not know, and you have to repeat the experiment and then finally come to a situation where you have some charge with you. That charge, that is called that amount of charge, which produces 1 dyne of force when two such charges are separated by 1 centimeter. The conclusion that I want to tell you is that K equal to 1 has no units. This has no dimension only in the CGS Gauss system, or we say ESU system. Either you write ESU or you write CGS Gauss system. So anything before 1800 time, so people have tried to manage the situation like this and fix the value of K equal to 1. But however, after the Maxwell's mathematical theory, the second idea has emerged. So now we are coming to the second idea. K will have the dimension. You should get familiarized yourself between the two unit system, that is CGS as well as the SA system for the case of electromagnetism. That is what I am trying to tell to you. Now we will not go into the detail of how we are going to fix this, how people have fixed this. No, that's a very long story. So how people have fixed this particular number of 1 divided by 4 pi epsilon naught, that I am not going to tell. But instead, if you are going to choose this kind of a K here, then if you write down the Coulomb's law, now K will be replaced by this. So you replace the K now by 1 divided by 4 pi epsilon naught. Then you write down Q1 Q2 by R square. You write in the similar way, but now what happens is there is a change. The change is that the force will be measured in 1 Newton. So now you have to write like this. So 1 Newton is equal to these numbers that you fill it out here. So here I am not going to do anything. It is the same thing. Let me copy here 1 divided by 4 pi epsilon naught into, now you are going to again redefine. Now this is very important. Whenever K changes, the unit for the Q changes. So now it is no longer stat coulomb. So now you are going to say that this is 1 coulomb of electric charge. Then you take another 1 coulomb of electric charge and then separate it. Now the separation distance happens to be 1 meter whole square. So this is the big difference that you have, which means that if you are going to have the two charges that you are going to keep it here, and then if you are going to separate them, now the distance should be 1 meter now, not 1 centimeter, because of the units, because of the base units that you are going to consider. Since you are going to consider SI unit, your experiment, it is not very simple. You have to repeat the experiment with 1 meter distance. Okay, the entire exercise has to be redone. Okay, it is while reading it looks so simple, but when you are performing experiment, you have to repeat the experiment with a 1 meter distance, and measurement of the force should be done in Newton, and then repeat this experiment. You remember this, repeat this experiment until the value of Q1 is such that I get a 1 Newton of force. Now that is the very important point you should remember. You take some amount of charge, do the experiment, and then note down how many Newton came. If it did not come to 1 Newton, change the value of Q1. That is Q1 equal to Q2. Remember that these two are equal, we are going to take. And you take the second Q2, which is equal to Q1, and repeat the experiment. If you are not getting 1 Newton, again go back here, change the value of Q, and then come back and repeat the experiment. You keep on repeating until you get 1 Newton of the force in your apparatus. There is a force measuring apparatus that should give you the 1 Newton. And the 1 meter you are always fixing, so that is not at all a trouble. If you are going to do that, whatever amount of charge that you dumped on this particular object that you are going to have here, I have put it as a dot here, no, this particular dot. So there, whatever charge that is there in that particular system is called 1 coulomb. That's what all people have done the experiment. Even then, you do not know what is meant by 1 coulomb. But people know that in the experimental apparatus, they have 1 coulomb of the charge. So till now, what we have seen is that in the case of the CGS Gaussian system of units, the constant of proportionality in the case of the Coulomb's law happens to be a dimensionless number, and in particular it has been fixed a value of 1. That is what we have seen. And contrasting to this situation, if you are going to redo this particular observation in the SI unit, we also have seen that the constant is dimensional parameter. That means it will have some dimensions. So we will see what is the consequence of this. We will write down the dimensions on both sides of this equation and then look at the situation. What is the consequence of having the dimensionless number, or what is the consequence of having a dimensional number? So where it is going to affect you, that we will be able to understand a little better if you can write down the dimension of this formula on both the sides. So as I have already written here in this particular case, this is representing the CGS system. Therefore, what I am going to write down here in this particular region will be based on the CGS system. So the force will be measured in dynes. So you know that in the CGS system, it has to be measured in the dynes. So therefore, I will write this. So if you are going to write the dimensional appearance, that means we will be writing in the square bracket to say that some quantity is dimension we are talking about. Then we can write like this. So on the left hand side, we have this dyne will be same as, or we can say that they are equal, by the way. If you want, you can say that that is equal to, K is dimensionless, so no need to write. And the coulomb in this case of in the case of the Q1, Q2, we know that we don't use the coulomb, but we will use the stat coulomb. So you write that. So stat coulomb, then multiplied by another stat coulomb, which means each one of them is 1, and divided by this happens to be centimeter square. So if you take if you rearrange this expression, if you cross multiply these two and then simplify, rearrange this, what we will be getting is the dimensions of the stat coulomb. Stat coulomb means what? It is the unit of charge that is being proposed under the CGS Gauss system of units. That is the stat coulomb. So that dimensions corresponding to that would be equal to, how do you simplify this? There are two stat coulombs are there here. Therefore, this will become square. Therefore, you take the cross multiplication and then take a square root. Then we can get this expression. Then we will be getting dyne to the power of 1 by 2. And then you get a centimeter here, which is for the length. And you will now simplify this dyne so that everything reduces to the fundamental unit. And dyne is basically what is meant by dyne. Dyne means you take 1 gram of the substance. Okay, you know in mechanics, so that's what I'm writing. 1 gram of the particular object should be accelerated by 1 centimeter per second. So you write down like this: 1 centimeter per second square. Per second square means, centimeter per second will be time differentiation. If you do, you'll get centimeter per second square. That is what I mean to say. This is equivalent to the dyne. Dyne means 1 gram of the material should be accelerated by 1 centimeter per second square. If that happens, that means you are actually applying 1 dyne of force. So based on that definition, we are writing it here. And then you have it to the power 1 by 2, and then you have a centimeter here. Of course, this is a small c. If you're not clear about it, we can write down in small. This c should be small letter. So that gives you this. If you multiply, we get gram to the power of half. Then you get centimeter to the power of 3 by 2. Then you get the seconds to the power of -1. So in the traditional notation means for the dimensions we used to write m for the mass, L for the length, T for time, right? So that is what I mean to say, MLT. If you want to write like this, then this is actually the mass. So we get to the power half. This is the length you will be having to the power 3 by 2. And this is the time to the power of -1. On the left hand side, you have the dimensions of the stat coulomb. And that's all. So this is one of the important results that you are having. So if you ask the question, what are the dimensions of stat coulomb? This is the answer. Okay, so our conclusion says that in the case of the CGS system, once again I'm telling that in the case of CGS system, because when you are moving to another system, this expression won't come. That's why I'm telling that in the case of the CGS system, as it is written here, the dimensions corresponding to the stat coulomb is given by mass to the power 1 by 2, length to the power 3 by 2, and time to the power -1. This is how the dimensions will look like. Now, what is the purpose of doing this is that we are going to ask a question now. The question is that how do you convert equation number 1 to the SI system? Is the conversion is simple or it's going to be a bit complicated? That is the question. Usually, what is the thing? Usual conversion, in mechanics, anything in the gram, you convert it to the kilogram. And anything in centimeter, you convert it to the meter. And for the second, there is no conversion. Same second is used. But however, this conversion is also not required if you are going to use the symbol m. Isn't it? So m is for mass. So when m is being written here for the dimension, whether it is the CGS system or in the case of the SI system, you use the same m. So basically there is no difference. And similarly, this being length, we simply write ml. So m and l will not change because of the CGS system or the SI system. So what is the meaning? If it is the case, do you believe that equation 1 in the SI system, if you are going to convert it, will remain the same. Do you believe like this? That is the question. Because just now I told you that gram to kilogram conversion, the symbol m doesn't change. Centimeter to meter, L doesn't change. If it is the case, what will happen to equation 1? M will remain as M, L will remain as L, T will remain as T. And therefore, do you believe? So there is a question is there. There is a question mark here. So you have to be careful. Here we are going to ask a question that whether equation number 1 written here will remain as such without any modification even for the SI system. Will it remain so or will it not remain? That is a question, and that's what we are going to see what will happen to this. Now to understand this, you have to rewrite this particular equation. Once again, we will consider this to let us understand this solution, or we will say answer. What is the answer that we are going to see? So we have a question now, whether equation 1 is going to be changed or will it remain same. That is the question. We will see the explanation. How do you understand this is that you have to rewrite this equation once again, namely the Coulomb's law you have to rewrite. Anyway, the equation is here. This equation being here, there is no need to write once again, but we will write down the corresponding units. So on the left side, instead of dyne, I will be having newtons. So Newton will be the force that we have, then will be equal to the dimensions of K, because we do not know whether it will have the dimension or not. But sometime back I already gave you the information that it will be going to have dimensions. That means K is a dimensional number. So whatever be the dimensions that you are going to put it there. And then Q1, Q2. Q1 will be in the coulombs, not in stat coulomb. Okay, so this is the one which is going to be modified and divided by, you get a meter square. This is the thing. And if you want to, now there are two things are there. If K, if you are going to say that Newton itself is equal to Coulomb square divided by meter square, then the K doesn't have any dimensions. Is this point is clear? If the Newtons is equal to Coulomb square divided by meter square, if it is so, then K will be dimensionless. But you already know that. But however, this is not true. So what is not true is that this particular equation that we have written here, Newton is not equal to Coulomb square divided by meter square. So this is the place where the not equal to is going to come. We will see how it is coming. And because of that reason means since these two things are not equal, K cannot be dimensionless. So that is, I will say like this. So that is this particular relation is not equal, and so K will be having dimensions. In the case of the SI system, what happens is you have the standard units corresponding to the mechanics problems. That means you know that there is a mass, there is a length, and there is a time, and which correspond to, you can write down simply, you can say that this is kilogram, then meter, and then a second. So that is fine. But these three are not sufficient to describe the electromagnetism. Only these three are not sufficient. You need something extra. Now that something extra is what we are going to plan to add. There is a three letters are there. We want to add a fourth letter here. Shall we add a C here? This C means Coulomb. That was the question. But however, people have done the repeatedly, people have thought about the choices that we can have. Shall we have the Coulomb or shall we have the ampere? Because electricity and magnetism are related. So because of that question, so the question is that shall we add a C here or can we add A here? So A is for the ampere. So the fourth letter, okay, this is the first letter, second letter, third letter. So we are our now discussion is on the fourth letter. So I'll separate it now. So this portion corresponds to the fourth letter that we are going to add. Shall we add a C or shall we add A? That was the discussion in the scientific community. Which one would be better? And final conclusion is that people have chosen ampere to be an appropriate choice. And therefore, what happens is you therefore write down the MK system. That means the so-called the mass kilogram second, mass kilogram second MK system. Then add a here. A is added for ampere. Capital A is added for ampere, and therefore this is known as MKSA system. And this one, there is an updating this particular system with some modifications, or that modification is actually called a rationalization procedure. Okay, that is exactly in the software industry we simply say it is updating. Okay, so specifically what has happened there is that rationalization procedure was done to this MKSA system, and that particular system is known as R. Then you write down MKSA. It is called rationalized. R means rationalized. But writing R, M, K, S, A is not at all good. So people have simply renamed this to SI system. Okay. This international system, that is what is written. Instead of saying IS, they have written SI because it is not a pure English. Okay. So that is the reason why it has come like that. So basic idea is now clear that you take the mechanics units, namely the MKs, only 3 of them, and then add one more thing for describing electromagnetism. So for electromagnetism, you need one more additional fundamental unit, and therefore totally you'll be having 4 fundamental units if you want to describe electromagnetism. So this is the first point, and after the rationalization, you have the SI system. And therefore, what is the consequence? So what is this explanation why I am giving this is that the question now is that we are now in a place to ask the question, what is 1 coulomb? Because that is the place where we have to provide a suitable answer in order to fix this. Okay, what is 1 coulomb? Only if you know the answer to this particular question, then we can fix the constant K in the Coulomb's law. If you don't know the answer to this question, what is 1 coulomb, we also cannot fix K. K will be hanging there without any number. So that is why all this discussion that I am explaining. So the conclusion for this question is that now in order to answer this question, now this particular SI system, that means it is a set of, for we say, group of scientists. They discuss together which one would be the better choice, whether the coulomb or the definition of the ampere, which one is better and why it is better. So these discussions have gone on into several years, and then people have come to a conclusion. The conclusion is that let us define, this is the conclusion, that let us define 1 coulomb. I will write only a capital C, enough now. COUL is not required. Let us define 1 coulomb is equal to 1 ampere multiplied by 1 second. So this is the definition. So I'll write down that this is the definition. So I'll write down DEF. So this equal to symbol represents a definition. Now, why I am putting a box here is that we have not derived any equation and then putting a box. No, usually in mathematics, that's what you do. You derive something, get a formula, and then put a box. The point here, reason for putting a box here is that this is the basic defining equation. Only if you have this equation, you can do anything further. This is a very key point. Key point means this is the starting point or the defining equation. Such equations are known as defining equations. So the terminology is important. Defining equations are very important. This is the defining equation. If you remove the 1 in this equation, because every time you don't have to write 1C, simply because 1s are cancelled everywhere, then you can say that the coulomb is equal to ampere into second. Okay, you should not read as AS. Usually there is no need to put a dot for the multiplication, but for convenience, if you want, you can write like this, A into second S. So it is ampere times a second. So this is the defining equation. C is equal to ampere into second. So this is the conclusion that has been made in the case of the in the committee that decides which units should be written how. Okay, there is a international committee that decides, and based on that, every other person follows that. Okay, if there is any trouble in that particular system, people again ask for changes, and then it goes through several changes after it is acceptable. Okay, so you should remember, this is not a small history. The SI system evolution, if you see, something like 1860, roughly around that time, you got this CGS system, CGS ESU system, electrostatic unit system. And sometime in 1960, because plus minus 5-10 years maybe that's okay, but I am telling you in the easy way to remember, 100-year gap is there. 1960, you got the SI system. I'll write down that this is known as the RMKSA system. So that is the time where it is started. It is not developed yet. That 1960 is the period where people thought that, okay, let us just modify the CGS and let us come to a new system, and we will call that as a rationalized MK system. So that was the proposal in 1960. And in 1983, there was some considerable modifications were there, and then people have given a proper name called SI system. And after 1983, of course, there may be some minor modification in between, but in the recent modification in the 2019. So here you have a more update, an update in defining ampere. So every time when I'm writing some year, some changes are there. So what are those changes? You can always open the document and read. But what I'm trying to say is that you see the historical period from 1860 onwards, people are working with units. 1960 SI unit started. 83, of course, some big modifications were there. And in 2019, because I want to tell you, because recently it has been done, and in particular related to ampere, because we are now studying electromagnetism. So there is a redefinition of the ampere. So ampere has been redefined when compared to 1983 definition. Okay, which means what I mean by that is, any definition that you have studied in the school is now changed. Okay, you might have studied, your schooling is certainly before 2019, isn't it? And therefore, any textbook that is written will be based on 1983 recommendation. So now the definition has been changed, and the change is based on the electronic charge. So we are now coming to the in the yesterday's class discussion, that the whole thing got improved only after people discovered what is the charge of an electron. That means discovery of the electron followed by calculation of the charge of the electron. Now that charge of the electron is going to define what is an ampere. That is what is going to define an ampere. That was not the story in 1983. In 1983, ampere was defined based on the force between two current carrying conductors. Now that definition is rejected. Rejected means what? It's okay, it will work, but the improvement is there. When compared to that definition in 1983, this present definition based on the electronic charge of electron works better. It's more accurate. Works better means, what do you mean by that is, the accuracy of writing certain things. Physics deals with numbers. Accuracy of the number is very important. So when compared to the previous definition based on the force between current carrying conductors, the present definition based on the charge of the electron happens to be much more accurate. And therefore, in the 2019, it has been proposed that we will be using the definition based on the electronic charge. So that is why in the last in the last class or so, I've been explaining the Millikan's explanation, and then his discovery of the electron has been very important in redefining the electromagnetic units. This is very important. Overall, if you see, it appears to be too simple, but these developments are very important if you want to gain some knowledge. And at the same time, you should also be very careful to remember that the CGS Gaussian units are very important in electromagnetic theory. So therefore, don't reject the CGS system. CGS system is also important. You should be able to jump from one system to another system at any time. Okay, coming back to this, our place here. So the question is that what is 1 coulomb? The answer is this: 1 coulomb is nothing but 1 ampere of current passing in 1 second. That means if you have a wire like this, and in this wire, suppose if 1 ampere of current is flowing like this in 1 second of time, that means you take a photograph only for 1 second. You see that this many number of electrons are present in the system. Then the total charge that was present in the system, this total charge, each one will be a Q1, Q2, Q3, Q4, etc. And remember that each one of them being electron, all of them are identical Q. Okay, even though just for mathematically I'm saying Q1, Q2, but everything is going to be Q here, Q here, Q here, etc. Each one is nothing but the electronic charge. Because when the current is flowing in a wire, each one of them happens to be an electron. So I'll write like this. And in this region, what is the meaning of this bracket is from here to here. From here to here is your 1 second. In 1 second of the time, the electron is flowing here in 1 second. If you wait for one more second, what will happen? If you wait for one more second, these electrons won't be here. It will go to the further to the right side. New electrons will come here. So, which means that in any given time of 1 second, whether it is the present 1 second or the future 1 second, if you are going to take a snapshot using a camera, for example, okay, it's not possible to take such photograph, but imagine a situation that you are able to click a photograph so that you can see all the electrons. Such kind of imagination you keep, and then if you are able to see all those electrons there, then total number of charges that are present in the system will be the Q. So that is what we mean to say, that this Q will be equal to N times V, where N number of electrons are present in the system. And that quantity is what exactly is defined as 1 Coulomb. That is what all it means to say.